Driven by an insatiable curiosity to unravel the universe's deepest mysteries, humanity has embarked on a journey that defies the boundaries of time. We relentlessly pursue answers to questions that challenge the very fabric of reality. Recently, the James Webb Space Telescope, with its piercing gaze, has captured an extraordinary glimpse of a structure older than the stars themselves, a cosmic anomaly that appears to predate the universe as we know it. This discovery raises profound questions. How can a structure exist that is older than the universe? Does this challenge our understanding of the Big Bang Theory? Join us as we delve into the incredible finding made by the James Webb Space Telescope, a 13.8 billion-year-old structure, which raises significant implications for cosmology. Imagine observing the vast expanse of the cosmos, where stars and galaxies perform a mesmerizing dance of light and gravity, revealing the secrets of both the past and the future. This is what the James Webb Space Telescope does regularly, capturing and transmitting stunning observations back to Earth. Recently, the telescope unveiled a breathtaking discovery, a 13.8 billion-year-old cosmic structure that challenges the very foundations of our understanding of the universe. This revelation has sparked heated debates and discussions within the scientific community as experts attempt to unravel the mystery behind this ancient phenomenon. One of the most pressing questions is how the James Webb Telescope could detect a structure older than the universe itself. To answer this, we must first explore what this structure is. It isn't a galaxy, nebula, or black hole. It's a star, a very old and very unique star, known as HD 140283. Or the Methuselah star. It lies more than 200 light-years away, near the Libra constellation. The star's name comes from the biblical figure who lived for 969 years, a fitting moniker given the star's incredible age. What makes the Methuselah star so fascinating is not just its age, but its speed. It zooms through space at over 800,000 kilometers per hour, revealing a dramatic history. Centuries ago, the precursor to our Milky Way galaxy consumed a dwarf galaxy, which was the Methuselah star's original home. However, the star's age is what really raises eyebrows. Initial estimates suggested it was around 16 billion years old, but the most recent calculation places it at approximately 14.46 billion years, with a margin of error of 0.8 billion years. This age presents a paradox because the current estimate for the age of the universe, based on observations of the cosmic microwave background, is approximately 13.8 billion years. How can a star be older than the universe itself? This conundrum has led to a series of speculations. Could the star be a remnant from a past universe? Might the universe be older than we think? Or could there be issues with the dating methods we use? To explore these possibilities, we must understand how astronomers determine the age of stars. Estimating the age of a star is an intricate task. Stars like our Sun maintain their brightness, temperature, and size for billions of years, making age determination difficult. Astronomers rely on subtle changes in a star's brightness and color over time, comparing these observations with mathematical models that predict how stars evolve with age. One key indicator of a star's age is its rotational speed. Stars slow down over time due to friction, and by comparing the rotational speeds of stars of different ages, astronomers can estimate their ages. This method, known as gyrochronology, is one of the tools used to gauge the age of a star. Another indicator of age is magnetic activity, such as flares and bursts of energy on a star's surface, which decreases as a star ages. Advanced techniques like astroseismology, which studies vibrations on a star's surface caused by waves traveling through its interior, have been developed to refine age estimates. For example, this technique was used to determine the Sun's age to be around 4.58 billion years. In the case of the Methuselah star, its age was estimated by considering the population of stars it belongs to. Stars can be categorized based on the amount of heavy elements, or metals, they contain. Our Sun is a population 1 star, rich in heavy elements. In contrast, the Methuselah star is a population tube star, with far fewer heavy elements, particularly iron. This suggests the star formed before most heavy elements were created in the universe, which happened during the explosive deaths of massive stars known as supernovae. There is also a theoretical class of stars called population Thebe stars, which are thought to have formed shortly after the Big Bang and contained virtually no heavy elements. The existence of the Methuselah star raises a perplexing question. How could it be older than the universe? The answer is not straightforward. It involves considerable uncertainty and assumptions. Based on measurements from the Hubble Space Telescope, there is a 70% chance that the Methuselah star's age falls between 13.66 and 14.46 billion years. There is a 15% chance that the star could be even older, but a 20% probability that it is actually younger than the universe's age. This uncertainty is akin to rolling a six-sided die and hoping for a 6. It's not very likely, but it's still a possibility. This assumption, however, ignores other potential sources of error or bias in the age estimation process. Nevertheless, it is clear that the Methuselah star is incredibly ancient, and it remains the oldest known star in the universe with a reasonably accurate age estimate. Rather than dwelling on whether the Methuselah star might be billions of years older than the universe, we can approach the issue from another perspective. Could the universe be older than scientists initially thought? Understanding 13.8 billion years is a difficult concept to grasp, but if we compress the entire history of the universe into a cosmic calendar with the Big Bang as the starting point, we might begin to reframe our understanding of time. Dark matter remains one of the most profound mysteries in modern science, challenging our understanding of the universe's composition, structure, and evolution. Unlike normal matter, which is made up of protons and neutrons, dark matter consists of non-ionic particles that do not interact in the same way with electromagnetic forces, making it invisible and detectable only through its gravitational effects. Various hypothetical particles have been proposed to account for dark matter, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. WIMPs are particularly well known as they frequently appear in theories beyond the standard model of particle physics and may provide an explanation for the observed properties of dark matter. Efforts to detect dark matter particles directly have been ongoing for many years. Experiments like the Cryogenic Dark Matter Search, CDMS, Super CDMS, and Xenon aim to detect interactions between dark matter particles and normal matter using highly sensitive detectors buried deep underground to shield them from cosmic radiation. Despite setting strict limits on the possible properties of dark matter particles, these experiments have not yet been able to definitively identify them. In contrast, indirect detection methods focus on looking for the results of dark matter annihilation or decay, such as gamma rays, neutrinos, or high-energy photons. Observatories like the Fermi Gamma-Ray Space Telescope and the High-Altitude Water-Cherenkov (HAWC) Observatory are actively searching for such signals from regions of high dark matter density, such as the centers of galaxies or galaxy clusters. Despite extensive efforts, the exact nature of dark matter remains elusive. Its properties, such as mass and interaction strength, continue to be subjects of intense research and debate. The quest to understand dark matter is not only about uncovering the components of the universe but also about testing fundamental physical theories beyond the standard model and gaining insights into cosmic structure formation. According to the Lambda Cold Dark Matter (Lambda CDM) model, dark matter plays a crucial role in the formation of galaxies and galaxy clusters. Small quantum fluctuations in the early universe grew under the influence of dark matter's gravitational pull, eventually leading to the large-scale cosmic structures we observe today. Simulations based on the Lambda CDM model predict how galaxies and galaxy clusters evolve over billions of years, and these predictions align remarkably well with observational data, reinforcing the idea that dark matter is a key ingredient in the cosmic web structure. The influence of dark matter extends beyond individual galaxies. It affects the dynamics of galaxy clusters, gravitational lensing of distant objects, and even the large-scale distribution of galaxies across the universe. By studying these effects, cosmologists can infer the distribution and properties of dark matter on cosmic scales, providing essential insights into its role in shaping the universe's evolution. Recent advances in observational techniques have enabled astronomers to map dark matter's distribution with unprecedented detail. Gravitational lensing, for example, uses the bending of light by massive objects like galaxy clusters to indirectly map the gravitational field of dark matter. Telescopes like the Hubble Space Telescope and ground-based observatories have conducted deep surveys to study these lensing effects, revealing intricate patterns of dark matter around galaxies and clusters. In addition to gravitational lensing, galaxy surveys provide another valuable tool for studying dark matter by measuring the motions of galaxies within clusters and their spatial distribution. By analyzing the gravitational effects of dark matter, surveys such as the Sloan Digital Sky Survey (SDSS) and the Dark Energy Survey (DES) have mapped millions of galaxies across the universe, uncovering the cosmic networks dominated by dark matter. Moreover, upcoming observatories like the Vera C. Rubin Observatory, formerly LSST, will conduct a decade-long study of the entire southern sky, capturing exceptionally deep, wide-field images to explore dark matter and its impact on cosmic structure formation. Beyond observational astronomy, theoretical physicists continue to explore alternative gravity theories and modified forms of dark matter. The modified Newtonian dynamics (MOND) hypothesis suggests that gravity behaves differently on large scales than predicted by general relativity, potentially explaining the observed dynamics of galaxies without invoking dark matter. Other theories, such as modified gravity (MOG) and scalar field dark matter (SFDM), propose alternative explanations for dark matter's gravitational effects. SFDM, for instance, suggests that dark matter consists of ultralight scalar fields that form a Bose-Einstein condensate, exhibiting wave-like properties on cosmic scales. Although these alternative theories remain speculative, they highlight the complexities and uncertainties surrounding the nature of dark matter and its role in the universe. Resolving these questions will require a combination of innovative observational strategies, theoretical advancements, and interdisciplinary collaboration across astronomy, particle physics, and cosmology. In summary, dark matter stands as one of the most important unresolved mysteries in contemporary science. It challenges our understanding of the universe's structure, evolution, and fundamental physics. Its presence significantly influences large-scale cosmic structure formation, gravitational dynamics, and the fate of galaxies over billions of years. As observational capabilities and theoretical models continue to advance, the search for dark matter remains at the forefront of astrophysical research, promising to offer profound insights into the true nature of our universe. Astonishing New Year's firecrackers on Earth wouldn't be visible until late December, and humanity's recorded history would span only the final 10 seconds of December 31st. Scientists determined the age of the universe by observing the light from stars born just a few 100 million years after the Big Bang. As the universe expands, it stretches this ancient light, making it appear redder, a phenomenon known as redshift. By measuring both the distance and the redshift of these stars, researchers have been able to estimate the universe's age. However, recent discoveries from researchers at the University of Ottawa suggest that the universe might be much older than previously thought, possibly around 26.7 billion years old. Renata Gupta, a physics professor at the University of Ottawa, revives an old theory by Swiss astronomer Fritz Zwicky from 1929. This theory posits that photons lose energy as they travel vast distances through space and time, which contradicts the observable redshift data. Gupta argues that by accepting this theory, alongside the expanding universe, redshift can be seen as a combined phenomenon, not just the result of cosmic expansion. Gupta's estimation of the universe's age at 26.7 billion years comes from combining the drained light theory with evolving coupling constants, first proposed by theoretical physicist Paul Dirac, which suggests that the fundamental forces in nature, such as gravity, might have changed over time. It's important to note that scientists have frequently revised their estimates of the universe's age. For example, in the 1920s, Edwin Hubble believed the universe was only about 2 billion years old. As methods and technologies have improved, our measurements have become more accurate, but doubling the universe's age is a huge leap. Whether astronomers will adopt Gupta's work remains uncertain, but one thing is clear. Regardless of whether humanity's written history represents 10 seconds or 5 seconds of the universe's grand timeline, the cosmos is incredibly old and awe-inspiring. Shifting from the age of the universe, there are some fascinating observations about the Milky Way. Recent measurements show that stars at the edge of our galaxy are moving much slower than stars in similar positions in other galaxies. There are several potential explanations for this phenomenon. One possibility is that our galaxy contains a very small amount of dark matter, the invisible substance that influences the gravitational structure of celestial objects. Another possibility is that our understanding of dark matter, especially its quantity, could be completely wrong. This mystery comes from data gathered by the European Space Agency's Gaia satellite, which has provided detailed information on the positions and velocities of nearly 2 billion stars in the Milky Way. These precise measurements have led astronomers to rethink what they know about dark matter and its role in the universe. Dark matter remains one of the most intriguing and elusive mysteries in modern astronomy. Unlike ordinary matter, which makes up stars, planets, and everything we can see, dark matter is invisible and doesn't interact with electromagnetic radiation. Its presence is inferred from its gravitational effects on visible matter and cosmic microwave background (CMB) radiation, suggesting that dark matter constitutes about 27% of the universe's total mass energy content. The concept of dark matter was first proposed by astronomer Fritz Zwicky in the 1930s when he noticed that galaxies in distant clusters were moving so fast that they should have torn apart if only visible matter was holding them together. Zwicky hypothesized the existence of hidden dark matter to explain this gravitational anomaly. Decades later, further evidence for dark matter came from studies of galaxy rotation curves, gravitational lensing, and the large-scale structure of the universe. One of the most compelling pieces of evidence for dark matter comes from observations of the cosmic microwave background radiation, which is the faint afterglow of the Big Bang. Small variations in the CMB provide clues about the early conditions of the universe and the distribution of matter, allowing researchers to estimate the amount and distribution of dark matter across cosmic scales.